Hi guys, and welcome back to my channel, Mr. T, Chem-MrT with Mr. T. So, a common thing that gets requested a lot of the time is balancing equations. So we're going to have a little look at this now. What we're going to be learning about is what all the parts of a simple equation show us, and how to balance a chemical equation. Okay, so how to balance them. So we're going to look at what is in a simple equation, what those things are, and how we balance a chemical equation. Something that a lot of people struggle with, balancing equations at first. I remember when I first started doing chemistry, when I was like 14, 15 and started to look at balancing equations for the first time, I struggled with them at first as well. And looking back at it in hindsight, it's because they're actually really super easy. And I assume that because it was in science, and science is quite a hard subject, it couldn't be that easy and I must be doing something wrong. And I think a lot of people do this, whether they're consciously aware of the fact they're doing it or not. They decide that this is too easy, the way they're thinking about it, therefore it can't be right, therefore they don't understand it. And no, it really is super easy. And with practice, eventually, one day, even if you're someone who's really struggling with it, with enough practice, it'll just click and you'll get it and you'll be like, oh yeah, this is really easy. I don't understand why I struggled with it. So trust me and trust in yourself. You can get there and you will get there. So, simple equations. What they show us is they show us a chemical formula of the things that are involved or made in a chemical reaction. So the reactants and the products. They show us the chemical formula for those, and what atoms and what elements are involved in them. And they're very useful in chemistry because we can work out how much of a reactant we need to make a given product, or if we say we've got, 10 kilograms of a certain reactant, how many kilograms of our second reactant are we going to need to make a product, so we're not wasting things. So really important for industrial purposes and for research purposes. And they crop up in almost every single area of chemistry. In the chemistry syllabus, no matter which exam board you are studying, chemical equations and balancing them can come up in almost all the different topics. They can also come up in biology as well, the big example being respiration. And sometimes we'll be able to make these from the word equation if we've been given things that we know already. However, we may also be given an equation in the exam and it might say balance this equation. Okay, so these are two ways that we could possibly do it. So we're going to have a look at what the parts of this simple equation show us, and what we're going to look at is we're going to look at the oxidation of carbon to make carbon dioxide. So this could be, for example, the burning of charcoal in a barbecue. So charcoal is mostly carbon, and the reaction that's going on, that's generating all the heat that cooks, is oxygen is combining with the carbon to make carbon dioxide. And the word equation is as such, so carbon plus oxygen makes carbon dioxide, and we can turn that quite easily into a simple equation. You should be able to do that now, so put the video on pause and try and make yourself a simple equation of this reaction. So carbon is C, oxygen is O2 because oxygen as a gas floats around as a diatomic molecule. Carbon, because it's a large molecule, it's a solid, it's just C. And for carbon dioxide is CO2. And I've put these in different colours and we'll see why now. So elements, things like C and O, so carbon and oxygen here, but also iron, Fe and Pb, lead, are just one symbol. Okay, so just one capital letter and one lowercase letter if they've got a lowercase. So you can tell if a chemical formula is an element or a compound, because if it's an element, it will just have one capital letter. For example, Fe, Pb, Cu for copper. So they are capital letter at first, followed by a lowercase letter. That means it's an element. The state symbols, which are in blue, you might also see these in subscript, so the same kind of size and positioning as the numbers here. The state symbols, which are in blue here, are all lowercase, and they follow the formula, and what these show us is they show us what state it is. So for example, AQ is aqueous. Now aqueous means something is dissolved in water. S is solid. and you can probably figure out that G is gas and L would be liquid. Now the compounds in this kind of very brown colour here. Compounds have got more than one capital letter in the formula. For example, capital C, capital O for carbon and oxygen. Very important not to write this as capital C lowercase o, because that would be the chemical symbol for cobalt. So each capital letter is the start of a new element. So C, carbon, O, oxygen. Okay, so we've got two oxygens here because we've got a 2 after it. In carbon monoxide, we've got CO, 1 carbon, 1 oxygen. CO2, 1 carbon, 2 oxygens. PbSO4, capital P followed by a lowercase b, so that is 1 element, so that's lead, Pb. S, sulfur, 1 of those. O4, so 4 oxygens. So 1 lead, 1 sulfur, 4 oxygens. So each capital letter shows the start of a new element in the compound. The subscript numbers that follow either compounds or elements show how many of that element are present in the compound. If there is no number, then for example like the carbon, it's just 1. So here we've just got 1 carbon. Here there's no number after this carbon here, so there is just 1 carbon. So the number refers only to the elements that they follow directly. So for example in carbon dioxide here, the 2 follows the O directly, so it only refers to the oxygen. So there are 2 oxygens, 1 carbon. In H2SO4, sulfuric acid, that means we've got 2 hydrogens because a 2 follows a hydrogen. We've got 1 sulfur because there's no number after the sulfur, so if there's no number that means there's 1. And then we've got O4, which means there's 4 oxygens. So 2 hydrogens, 1 sulfur, 4 oxygens. Now, if we have another look at another equation, so we've got here a balanced equation for the reaction between hydrogen and water. So you might see this written out here. And we can see we've got 2 as a big number in front of H2 here, the hydrogen, and we've got 2 as a big number in front of our water, H2O here. Now this shows us how many of each of those things we have. Okay, so how many of each of the following things that we have. So 2H2 means we have 2 hydrogen molecules, 2 H2 molecules. So that means we've got 4 hydrogen atoms in total, because we've got to take this 2 and multiply it by this 2. So 2 times by 2 equals 4. So we have 4 hydrogens in total in 2H2. When we look at the 2H2O on the other side, that tells us that we've got 2 H2O molecules. So we've got 2 lots of H2O. So if we've got 2 lots of H2O, we've got 2 times 2 hydrogens. So we've got 4 hydrogens again. But we've also got now 2 times by 1, because there's no number after the oxygen. If there's no number after the oxygen, we imagine there's a 1 there. So 2 times 1 is 2 oxygen atoms. So 2 H2O, 4 hydrogens, 2 oxygens in total. Now, some rules for balancing an equation. In a symbol equation, we must show exactly the same atoms on each side of the arrow, so the reactants should have exactly the same number and type of atoms as the products. No new atoms are going to get made, so there's nothing going to be appearing extra on the right hand side. And no atoms can vanish, we can't make them disappear either, they've got to stay the same. And it's just counting. Okay, so all we have to do is be able to count with a little bit of multiplication. If we have the same number of elements on each side of the equation, on the reactant side, on the product side, then the equation's balanced and we're all good. If the equation is not balanced, we can only adjust how many of each molecule we have. So in the previous example, we can have 2 lots of hydrogen molecules, 2 lots of water molecules. What we can't do is change the chemical formula. So for example, we can do 2H2O, 3H2O for example, but we cannot do H2O2. And that is a very, very important point. Okay, so we can't change the molecule. The reason being is H2O is water, H2O2 is a different compound. We're changing the chemical compound, and that is incorrect. That is wrong. That we cannot do that in an equation. Hydrogen peroxide, by the way, is often found in hair dye and things like that, or hair bleach, and it's highly toxic, and you wouldn't want to drink it. Which leads me nicely to a chemistry joke, which two men walk into a bar, and the first guy goes up to the barman and says, "Hi, can I have a glass of H2O, please?" And the barman slides him a glass of water and turns around to the friend, "And what will you have?" And the friend says, "I'll have a glass of H2O2, please." Drinks it and dies. Another example, another reason why we can't do this, okay, or a better explanation of why we can't do this than just talking about it in words. So here we've got a chemical equation which isn't balanced. We've got magnesium plus oxygen makes magnesium oxide. And we can do a very quick count. We've got one magnesium, two oxygens, O2, two oxygens on this side, one oxygen on this side. So we've got to do something to balance this equation. Now we can represent the magnesium as a grey sphere and the O2 as two red spheres. Okay, so each of these spheres is showing one atom. So we've got one magnesium atom, two oxygen atoms, which is what the equation is telling us. And then on the other side, we've got an oxygen and a magnesium joined together in magnesium oxide. Now we can't just make MgO2 because that would be changing this chemical formula, and we can't do that. Okay, so we can see it's not balanced. We've got too many oxygens on this side, not enough on this side. So what we can do is we can make two lots of magnesium oxide. So we've got one lot of magnesium oxide here, one lot of magnesium oxide here. So we've got two lots of it in total, which now means we've got two magnesiums, and two oxygens represented by the red spheres. Now we can see that the number of oxygens on each side is now the same. We've got two on the left hand side and we've got two on the right hand side. But now the number of magnesiums is wrong. We've got two magnesiums on this side but only one on this side. So we need to do something to this magnesium up at the top on the left hand side to balance it out. Now we can't do Mg2 because that would be changing the chemical. What we can do is give two lots of magnesium by putting the big number 2 in front of it. And now the equation is balanced. We've got two magnesiums on the left hand side, two magnesiums on the right, two oxygens on the left hand side here, and two oxygens on the right hand side. And that equation is now balanced. Another example, going back to the start, one of the ones we looked at the beginning. So we've got carbon plus oxygen makes carbon dioxide. To see if the equation is balanced, we need to count how many of each element we have on each side. Okay, on each side of that arrow. My recommendation is you start on the far left of the equation and work your way across, just because that's a logical, ordered way to do it. And you can also, while you start off and practice and start to learn how to do the balancing equations, set out a table a bit like this one here. So I've got our reactant elements, carbon and oxygen, and I've got our product elements, carbon plus oxygen. The next step is to start counting how many of each that we've got. So we're going to start with carbon. We've got just one carbon by itself. There's no number before it, there's no number after it, so that means we've just got one carbon on our reactant side. We cross over to our product side, and again there is no number before the carbon, there is no number directly after the carbon, so we've still only got one carbon. We've got one on each side, so it's balanced. Next step, the oxygen. We've got O2, so that means we've got two oxygens, this time on our reactant side, and on the product side, again, we've got O2. So again, we've got the same number of oxygens on each side, so they're balanced. Because all the atoms are balanced, the equation is balanced. Nice and simple. Moving on to our next example of H2 plus O2. makes H2O. We've already seen this balance, but we're going to look at how you could balance it if you didn't know it already. Again, same table. Again, we fill in the elements that we have. So we've got H and we've got O, and they're the only two elements that we've got. And we start with the number on our reactant side. So we've got H2 here and H2 on this side. So we've got 2 on our reactant side of hydrogen, and we've got 2 atoms of hydrogen in our product side. And so that's balanced, they're the same. Now to look at the oxygen. On our reactant side we've got O2, so we've got 2 of those. And on our product side we've got H2O. There is no number directly after the O, so we've only got 1 of them on our product side. So this isn't balanced. So how can we balance this? We can't make H2O2 because that would make something else, but we do need 1 more oxygen. Just to reiterate, we cannot make H2O2 because this would change water to hydrogen peroxide, and that's a completely different chemical. We can't change the chemical. What we can do is add more molecules. Now you'll notice we've got 2 oxygens on the left hand side, 2, and 1 on the right. So we need 1 more oxygen on the right hand side, or we need to double the amount of oxygens on the right hand side. To do that, we can put a big number 2 in front of the H2O, which says we've got 2 molecules of H2O. Now we can put this into a new equation. Okay, so here's our equation. H2 plus O2 makes 2 H2O. This is our first step in balancing the equation. We know our products are our reactants are exactly the same because we've not done anything to change those. We've only changed our reactant molecule here. So now we need to count again on this side the number of elements. So we've got 2 H2O. That means we've got 2 H2O molecules. To work out how many hydrogens we've got, we take this number and multiply it by this number. So 2 times 2 is 4 hydrogens. So we've got 2 on our reactant side now, 4 on our product side, so it's not balanced. Look at our oxygens. We've now got 2 times by the 1 that we originally had, which is 2. So the oxygens are now balanced, but the hydrogens aren't. So it seems that we've made no progress, except we have. Okay, so we've balanced our oxygens. Although our hydrogens aren't balanced now, we can see that we've got double the amount of hydrogens on the right hand side compared to the left hand side, so we need to double the amount of hydrogens on the left hand side. So we do that by putting a big number 2 in front of the H2, and that gives us 2 times 2 hydrogens on the left hand side, which is 4, 2 times 2 hydrogens on the right hand side, which is 4, so it's balanced. Okay, another example. This is the Haber process reaction, a very important reaction for all of chemistry and for all of humanity, in fact, because it makes fertilizer, which most of our food relies on. So the reaction is N2 plus H2 makes NH3. So again, exactly the same way, we're going to start counting out the elements. So we've got 2 nitrogens, 2 on this side, 1 nitrogen on this side, because there's no number directly after it, so it's not balanced. We've got 2 hydrogens here, H2, but we've got 3 on this side because it's got NH3, so it's still not balanced either. Now neither of these are balanced, so we need somewhere to start. My first step is to start with nitrogen. A, because it's the furthest on the left hand side, and B, because it's the simplest to look at, following the same process as before. We've got double the amount on the left hand side, our reactant side, compared to the right hand side, our product side. So we need to double the amount of nitrogen on the right hand side. And again, we can't go N2H3 because that would be changing the molecule. So we can only put a big number in front of it. So 2NH3. So now this has changed only the number of products elements that we have. So we've now got 2 nitrogens, 2 times by 1, there's an imaginary 1 there, 2 times by 1 is 1. So it's now balanced. And we've got 2 times 3 hydrogens, which is 6 hydrogens. So the hydrogen's still not balanced, but we've balanced the nitrogens. So what can we do next? Very easy fix. We can see 2 to 3. What would we need to times 2 by? 2 to 6. What would we need to times 2 by to get to 6? And the answer is 3. So we need to triple the amount of hydrogen on this side because we've got triple the amount on this side. So we put 3H2 into the equation. And when we do that, 3H2, 3 times by 2 is 6. So we put that down this box here. 2 times 3 is 6. 6, and that equation is balanced. Slightly harder example, but we do it in exactly the same way. It's a reaction between aluminium and bromine to make aluminium bromide. Counting the elements shows that aluminium is already balanced, 1 on each side, but the bromine isn't. We've got Br2 here, so 2 bromines, and Br3, 3 bromines on this side, so it's not balanced. Now, it might look, if you're mathematically minded, it might look really obvious about what the answer is. However, if you're not, it doesn't matter too much. All you have to do is find the lowest common multiple of 2 and 3. So what is the lowest number that 2 and 3 can both multiply by to get into? So 2 times 2 is 4, so it can't be 4 because 3 times 2 is 6. 2 times 3 though is 6. I'm not going to show you how to find lowest common multiples, it's a maths lesson. Something you should be able to do by GCSE, I think. And the answer is 6, but 6 is the lowest number. So essentially those two numbers times together. If you're unsure about how to find lowest common multiples, what you can do if you've got two things that are not double or triple is just times these two numbers together. So 6. Now what that tells us, it tells us how many bromines we should try and have on each side. So we should aim to have 6 bromines on each side. So Br2, we've got 2 bromines, so we need to multiply 2 by 3 to get 6. So we should have 3 Br2. On this side we've got 3 bromines, Br3, so we need to put a big number 2 in front of there, 2 AlBr3 to get us 6 bromines. And here we go, this is what that looks like. So now we've got 3 times 2 equals 6 bromines on this side, and 2 times 3, 6 bromines on this side. Okay, so all balanced. But now the aluminium's not balanced. We've got 1 on this side and 2 on this side. But you should be able to fix this easily. Have a little go, have a little think, and see how you can do it. Put the video on pause. And what you should have is 2Al plus 3Br2 makes 2AlBr3, and that's our balanced equation. We've got 2 aluminiums here, 2 aluminiums here. 3 times 2 equals 6 bromines here, 2 times 3 equals 6 bromines on this side. Now sometimes you might see something in brackets. A species in chemistry just means an atom, a group of atoms, ions, compounds, anything that's basically a chemical. And here is our example equation. Now if this looks really complicated to you, don't worry, it's exactly the same process and we're going to explain how to do it. So we've got HNO3, which is nitric acid, plus magnesium hydroxide, MgOH2, makes magnesium nitrate, MgNO3 plus water, H2O. So we can see we've got the magnesium hydroxide, MgOH2, and magnesium nitrate, which are in brackets. So what does this mean then? The brackets mean that the elements within the brackets are joined together like a compound. So the OH sticks together, the NO3 stays together. The subscript number after it, both 2 in this example, so the OH2 and the NO3 close brackets 2, tells us how many of those groups of molecules that we have. So we've got 2 OHs, we've got 2 lots of NO3. So in 2 OHs we've got 2 times 1 oxygen, 2 times 1 hydrogen, so we get 2 oxygens, 2 hydrogens. In the NO3, 2 means we've got 2 lots of NO3, so we get 2 nitrogens and 6 oxygens. Okay, so they're in total joined together. Then, once you know this, balancing is exactly the same as before, so give it a go and see if you can do it, and we're going to work through it in a second. So put the video on pause if you've not already done so, and now we will have a look at how to do it. So again, set up in a table. You can see it's much bigger this time because we've got hydrogen, nitrogen, oxygen and magnesium in our equation. Then we've got oxygen and hydrogen again. Now when we're counting the number of each element, it's important to make sure you count all of the elements on each side of the arrow. So we've got one hydrogen here, but we've got two hydrogens here because we've got two lots of the OH. So we've got 2 plus 1, 3 hydrogens on the left hand side. On the right hand side, there's no hydrogen in this chemical here, the magnesium nitrate, but there is in the water H2O, so we've got 2 hydrogens there, not balanced. Next up, nitrogen. We've got 1 nitrogen here in the HNO3, but we've got 2 nitrogens here because we've got 2 lots of NO3. So 1, 2, not balanced. Now for the oxygens. We've got 3 oxygens here, 2 oxygens here, 5 in total, and on this side we've got 3 times 2, 6, plus 1, 7. So 5 on the left hand side, 7 on the right, not balanced. Then we've got 1 magnesium on each side, and that is balanced. So where to start then? Where to start? Easiest to solve at the moment is the nitrogen, because we've got 1 nitrogen on the left hand side, 2 nitrogens on the right hand side, so we know we need to double the amount of nitrogen on the left hand side. We can do that by putting a big number 2 in front of the HNO3, and this changes what's on the reactant side. So now we can count our way through. So we've now got 2 hydrogens here plus 2 hydrogens here, which equals 4 hydrogens, which isn't balanced. We've got 2 nitrogens and 2 nitrogens, which is balanced. And we've now got 6 oxygens plus our 2 oxygens, which is 8 oxygens, which isn't balanced. So we've balanced our nitrogens, hydrogen and oxygen still unbalanced. Okay, the oxygen looks tricky with 8 to the 7, but the hydrogen's an easy fix, so we'll start with that. We can see we've now got 4 hydrogens on the reactant side, 2 hydrogens on the product side, so we need to double the amount of hydrogens on our product side by putting a big number 2 in front of H2O. Now this is going to change the number of product elements we have. So the number of hydrogens now is 2 times 2 is 4, so that's balanced. Our number of oxygens is 2 times 1, which is 2, plus our 3 times 2, which is 6, which is 8 oxygens, so that's balanced. So although it looks really complicated, it's exactly the same process. We're just counting and doing simple multiplications. Okay, multiplying by 2, multiplying by 3, multiplying by 4, things like that. It's nothing too extravagant. So, little summary then. We must have the same number of atoms of every element on both sides of a chemical reaction. We can't create or destroy any atoms or any elements. We can only add a large number in front of an element or a compound. We cannot add small numbers, the subscript numbers, within a compound. Okay, that would be changing what the compound is, and we can't do that. So for example, H2O can become 2H2O, but never H2O2. Remember about the poor guy who went in and ordered a glass of H2O2 and then passed away. The large number means you have that many molecules of what follows. Okay, so for example 2H2O means you got 2 lots of H2O, so you got 2 times 2 hydrogens, 4 hydrogens, 2 times 1 oxygens, 2 oxygens. And balancing is easy as counting and using basic multiplication. It really is. You may not be thinking about it now. You may still be thinking, oh, it's still really, really difficult. But trust me, you will get there. You just need to keep practicing examples, looking at the answers, and then seeing where you've made your mistakes. It's just like riding a bicycle. The more you practice it, the better you will get. Once you've figured it out, once you've got it, that's it. You'll never forget it. It'll be really, really easy from that point onwards. So just like riding a bike, you just need to put that effort in until you crack it. Once you've cracked it, it will become super, super easy. I hope you found this video useful. There are plenty of good examples on the internet of questions. If you Google balancing equation questions, you will find loads and loads of relevant answers. So please go away and do that, and just keep practicing, keep practicing, keep practicing, and you will get there. Okay, take care guys. See you in a video soon. Bye bye.